Hi there. So we've introduced this notion of what a set is, and I want to start playing around with, with what we call set operations, because math teachers can't just leave things well enough alone. We start trying to figure out ways to combine things, right? That's why we have all those math operations. Before we get there, though, I wanted to make a quick notational thing. It's come up in the homework and stuff, and I want to make sure it doesn't throw anybody off. So there was a bit of notation, something like this. X is, then this funny symbol that looks kind of like an E, with, something like a capital letter like we usually use to represent sets sitting, right next to each other. So when you see that, that means that X is an element of the set A. So X is in the set A, right? I actually had a teacher one time who just wrote X in A instead of using the symbol. So other textbooks will sometimes use kind of a different symbol, like a slightly curly E. I prefer this one myself. So seeing X, with the E, that means X is an element of the set A. Similarly, you see like a slash through it, well, that means that X is not an element of the set A, because like not equal to, you've had to deal with that before. So I wanted to get that bit of notation out of the way so it didn't throw anybody off before we actually start talking about set operations and things of that sort. So give me just a sec to clear this off. All right. So I want to introduce these three set operations that we're going to be using as we make our way through this content on set theory. So in addition to listing these out, I want to sort of visualize them using the lovely whiteboard, flanked by the Pokeballs and whatnot behind me. So you may have noticed I posted a handout in our Moodle course that kind of lists these operations and kind of suggests, sorts of ways to kind of remember what's going on. It also talks about what we call a Venn diagram. So most of my students have ended up seeing Venn diagrams at some point in the past, but oddly enough, it's not usually in the context of a math class, which is where I saw them first. They end up popping up like in English courses and other things where you're talking about like comparison and contrast, that kind of stuff. So if you haven't seen a Venn diagram before, it's basically just kind of like a rectangular box. The board works pretty well for that. I've always kind of liked labeling because you're imagining, like I've said previously, you're imagining some sets that are subsets of some bigger guy. We generally refer to him as the universal set. Our book uses the letter U to reference universal sets. You might see like a capital Greek omega for that, but that does, for the purposes of our course, U is fine. And so then we'll end up representing subsets that live inside this bigger guy with circles. So we have, say, a subset A that lives inside the universal set U. And to be perfectly general, if we had another subset, we would generally draw it like this. So we have B over here. So that way there's some overlap, but if B were completely inside A, then we have that B is a subset of A, along with being a subset of the universal set, that kind of thing. This is sort of the general setup if you've got a pair of distinct sets. Like I said, if you had to do comparison contrast using a Venn diagram, you're familiar with this. So I wanted to talk through those kind of three set operations real quick. So the first of the bunch is what we would call the complement of a set, and that one doesn't actually need like a pair of sets. We can talk about the complement of A by itself. So the complement of A, you can think of it as kind of like an opposite. So if what's inside A is represented by this area I'm kind of waving my hands around right here, the complement is everything that's not in A, it's outside A. So all of this stuff, I'm not going to like waste a ton of marker ink, but imagine like if this were colored one thing, then you sort of like toggle the switch and everything outside A is colored to represent the complement. So hopefully that one makes sense. Our textbook denotes complements with like a little so a complement looks kind of like you got like a little apostrophe looking thing right there. Some textbooks would use like a superscripted C. I've seen other symbols. For our purposes, use that apostrophe guy. Anyway, so that's the complement of a pair of or of a set. So the other two set operations actually do rely on having a single or having a pair of sets. So we have the intersection, which we tend to write with like this little thing that looks kind of like an N for intersect. Hopefully that helps. So we have A intersect B, and the handout suggests you generally think of intersections. The first thing that probably pops into your mind is like a road, right? So this is like a piece of road where two guys cross, and it's part of both roads at once, right? So the intersection is what the two sets have in common, what appears in both sets simultaneously. So if I were wanting to shade in that intersection right there, it's that chunk that's kind of in the middle. So that's the intersection of a pair of sets. Again, what they have in common, what's in both, the overlap, however you want to look at it. So the last set operation that we want to take a look at is what we would call the union of a pair of sets. So the union of A and B, you can think of it like again, I suggest the idea that's always popped into my head is thinking of unions as in like marriage, because the union comes up in like the vows and stuff in the wedding ceremony. Two people becoming one unit in a sense. You might also think of unions as coming up in the context of like labor unions, where a whole bunch of people in a particular working in a particular field all get represented as one at like a bargaining table or something like that. So what you can think of in that instance, it's kind of like you're getting rid of the boundaries between the two sets when you form the union. So you can kind of imagine, I probably should have done this. Instead of having, hard lines, linking those guys up, the union is kind of like we just pretend they're not there, and A union B is now just one set that, is anything that's in either one of them. Do remember, the union by default includes the intersection. So, we'll talk more about the difference between, both, and exactly one when we get to some stuff in chapter 1. But for now, just remember, union includes intersection. All right, so that's kind of a little visualization here. Let me clean this up a bit. I want to take a look at a specific example of how you might use a Venn diagram to sort out some sets. All right, so for this next example, I actually want to have like specific sets. So this may not look terribly mathematical at the moment, but I promise we're really doing math stuff. So we want our universal set to be the months in our calendar year, and I want to make two subsets out of those guys. So I'm going to have the set T. So that's going to be the set of all months inside our universal set, which have 31 days in them. Okay. So then I'm going to have another set J. And that's going to be, unsurprisingly, maybe all of the days, all of the months in the year, whose name starts with the letter J in English. Nothing, don't try to play any language tricks with me. So T, all the months with 31 days. J are the months that start with J. And then we've got sort of, I want to populate the Venn diagram. All right. So you might kind of start by listing these things out in roster form. So as it turns out, months that start with J, you can, it's not, there's not many. You have January, June, and July. So we got those three. The ones with 31 days can often be kind of tricky. When I'm in the classroom with folks, I kind of like stopping and asking them which months have 31 or 30 days in them, and then watch to see who starts doing like something with their knuckles where you count across, or people singing like the little song because there's sort of a poem that ties into it. So for what it's worth, if you were to work this out here, so the 31 days, we have January, we have March, we have May, we have July, August, and let's see, October and December. Okay, so those are, sorry if the handwriting is a little tough to read, but hopefully, you can track down. Some folks will end up just like grabbing it, like they'll grab out a calendar and they start looking to see which ones have a 31 at the end. So anyway, so now if I were trying to fill in my diagram, what I need to do here is I usually kind of start like I do what sort of I call an inside out approach. But I sort of look and see, well, what belongs on the inside of this thing right here? So in this instance, well, what do they have in common? That's the intersection of my two sets, right? So if I look, January shows up in both sets. So does July. So, all right. So I know those two guys belong right there. Making my way outward, well, what else belongs in J? Well, I've already taken care of January and July, so all that leaves is June. I'm just going to write it out so it doesn't get confused with the January. My A and U can end up looking alike if I'm in a hurry. All right, so now I need the list inside this outside part of T, this little moon shape. I need everything else up here that I have not already accounted for. So that's March, May, August. This is going to get a little full. So let's see, then we have October and December. All right. So now at this point, we've accounted for everything that lives inside J. We've got everything that lives inside T. We haven't actually taken care of everything inside the universal set, though, because we still need what's outside of, like, both of them, right? All right. So now if we play around with this, well, let's see here. What else are we missing? We haven't taken care of February yet, or April, or September, or November. I think that's covered everything. Let's see. 1, 2, 3, 4, 5, 7, 8. Yeah, that's 12 months. So, all right. So I've got everything taken care of here. All right, so that's kind of an example of populating a Venn diagram with sort of individual, set memberships. So what I'm going to take a look at in our next video is, do we necessarily need to go to the trouble of filling out the Venn diagram visually? I mean, you can always do it, but maybe it's going to get a little dense. So, keep watching, and you'll get to see how we handle this, a different way.